Good morning, Milan. I'm Longfei Chen, a research associate at the University of Edinburgh. It's a great pleasure to introduce our work, OPPH, a vision-based operator for measuring body movements for personal healthcare. In Advanced Care Research Center of University of Edinburgh, we use computer vision-based method for helping older adults living safe and independently at their own homes. For example, we can do standard clinical tests remotely and automatically. We can detect critical events such as loss of consciousness or inactivity for a prolonged of time by analysis their body movement. Also, for longer-term healthcare conditions, we can monitor the deterioration of their movement and the recovery process after surgery. However, when applying the current computer vision-based algorithm in our experiment in detecting the human body movement, we find some limitations and issues. First, for small motions like finger movement at a distance like 2 meters, the pose-based key point estimation method struggle to detect the small motions like finger movement. But optical flow method can successfully detect those small movements. For a certain pose, like in the top middle picture, the person lying on a couch, the pose has a significant jitter in the key points in this pose, even the person is completely not moving. And for optical flow based method, if the pet is moving around the person or the tree leaves is moving as a background, the accuracy will be influenced for the person's body movement motion estimation. For both pose-based and optical flow-based methods, in low lighting conditions such as a person watching TV at night, they have a significantly noises in estimate the key points or the flow vectors. So those inaccuracy particularly influence when detecting the person stays motionless, which has a significant meaning in the healthcare. Here we conclude the challenges we face for real-world applications. First, the image sensor, especially under low lighting conditions, the errors are generally bigger. Second is for unseen environments or rare poses, it's hard to fine-tuning the algorithm for every new environment. The third is the data limitations. We're short of good labeling data for the body motion ground truth, especially for optical flow. Most are synthetic data sets. For real-world data sets, there are many focus on the active actions of human, while not sufficient to present the non-active human movement. So in this work, we have two proposals. First, we develop an operator to enhance the motion estimation method for healthcare applications, especially accuracy of the motionless of the person. The second is we create a real-world dataset of humans staying inactive or motionless. Because the real-world noises are diverse, it's challenging to model the different types of noises. So we focus on capturing the properties of a real body motion. So this operator first takes two consecutive images and takes their difference, then doing a thresholding in RGB domain. Um, this is based on that the real body movement will cause changes in brightness and color intensity. Then we goes to a spatial filtering. This is because the real body movement will usually form a connected area rather than isolated pixels like the noises. The next we goes through a temporal filtering to distinguish short-lived noises from the true body movement. Um, for the parameter of the operator, we'll optimize them using real-world data, including different lighting conditions from normal daylight to very low lighting, and also different home environments. To address the issue of lack of real-world human motionless data, we connect a dataset where people pretend to be completely motionless, and we take about 101 videos ranging from seconds to minutes in different scenarios, different body poses, and different camera views. Some videos also have paired present in the view. And for ground truth, we provide the human body masks. If you're interested in the dataset, you can visit the following website. To evaluate the performance of our proposed operator, we test on several different datasets and use the 2D body movement speed as a criteria. The first test is a JHMDB dataset, which contains 21 active actions of human. It provides the ground truth of human body parts, the optical flow, and the pose. On this real-world dataset, we find that our operator enhanced the pose estimation methods such as the VIT pose and HRNet for more than 1 pixels per frame, the less errors of estimating the 2D body movement. And for the optical flow methods such as raft or funnel bank, the operator slightly reduced the accuracy in this dataset. The second dataset we test is a large synthetic dataset as called serial. It contains both people being active or inactive synthetic human and realistic backgrounds. For this dataset, the operator proposed slightly improved for all pose-based method and optical flow-based method. Then we test the operator on our own human motionless dataset. With adding the operator, both pose-based or optical flow-based methods error rate is reduced to nearly zero. That means the operator is very efficiently distinguished from the noises and the real body movement, and very accurately it detects the motionless of the human body. Finally, for longer-term human body motion estimation related to the chronic conditions of the person's movement, we put the videos together for longer term for those two datasets and estimate the correlation with the ground truth. The result shows that with adding the operator to the best performed optical flow-based method, the operator can successfully keep the longer-term motion estimation. In conclusion, our proposed operator OPPH can effectively reduce the real-world noises for vision-based motion estimation methods and is suitable for crisis events or longer-term human body movement monitoring for healthcare applications. Finally, I want to thank my co-authors and the organizers of the workshop. It's been a shame that I cannot join you in person in Milan because of my visa issue. If you have any questions or comments, please feel free to contact the following email and visit our dataset page. This is the end of my presentation. Goodbye.